Hello everyone. Today I will be talking about better and simpler learning augmented online caching. To motivate our problem, I'll start by revisiting the foundational idea behind online algorithms. So what's the core component of our online algorithms is modeling decision-making under future uncertainty. The future uncertainty comes in because in the online algorithm setting, we have to respond to each input before receiving the next input. And how decision-making comes in is because the choices that we made in past rounds will affect the decisions we have available and the costs in future rounds. Examples of such online problems abound in computational settings. These include caching, scheduling, K-server, metrical task systems, among others. And in theoretical computer science, much of the work on online algorithms has focused around the design of online algorithms with good worst-case competitive ratio. So what this worst-case competitive ratio measures is the infimum over all possible inputs sigma of the ratio between an algorithm, let's say A, the algorithm A's performance on input sigma, and the optimal offline algorithm's performance on sigma. So I'll also take this as a chance to introduce some of the notation we'll be using in this talk. So our inputs will be sigma. We will use A, this calligraphic A, to denote algorithms. Alg sub A will be the cost of an algorithm on a given input. And opt will be used to both denote the optimal offline algorithm as well as the optimal offline algorithm's cost. And so the expression displayed is the worst case competitive ratio as our inf is over all possible input sigma. So as lovely as the worst case framework is for analyzing online algorithms, there are also several limitations. One limitation is that worst case algorithms ignore potentially useful structure that we can find in the inputs. And so if, for example, if there are patterns in the inputs or some sort of worst case never occurs, we don't really take advantage of these factors. Moreover, the predictions made by the worst case framework are oftentimes too pessimistic to inform practical decisions. This is because if we have two different online algorithms and both have the same worst case performance, it's still possible that one algorithm is a lot better in most practical settings on realistic inputs than another. And finally, this worst case objective can also tie our hands in terms of algorithm design by forcing us to sacrifice performance on easy, common inputs in order to have a marginally better performance for pathologically hard inputs. And these pathologically hard inputs might just never appear. So these shortcomings of the traditional worst-case analysis model for online algorithms has therefore motivated the exploration of various beyond worst-case models of online algorithms. These have included stochastic inputs for online algorithms, random arrivals, as well as semi-online algorithms. This talk will take a slightly different direction from these approaches and look at augmenting online algorithms with learned predictions. This has been a recent area that has received quite a lot of attention in the past couple of years. And we will continue the exploration of this area by looking at algorithms for the specific problem of learning augmented online caching. So how does the learning augmented online algorithm framework work? So online algorithms are fundamentally about decision-making under future uncertainty. And so with this framework, we try to reduce future uncertainty by using learned predictions. And so you can think of training a machine learning model to predict future inputs, and then using the predictions of this model to guide and optimize the decisions of our online algorithm. So one feature of this framework versus other approaches to modeling beyond worst case online algorithms is that here we don't make any assumptions about the structure of the input. And rather, we just assume that there exists a black box predictor that is able to predict future input well. And so another benefit is that in this model, you can actually verify the hypothesis that the predictor is accurate, whereas it is more difficult to verify the stochasticity of your input. And so with this model of online algorithms with ML predictions, our goal is to show results of the form that if the predictor's error is at most eta, then our competitive ratio is at most a function C of eta. And so what this means is that if our predictor's error is not too bad, then we can have an upper bound saying that our competitive ratio is not too bad either. To make this a little more concrete, I'll define two objectives that we want our algorithm to satisfy, and these objectives have been common to most of the recent work on learning augmented online algorithms. The first objective is consistency, that if the prediction error eta is small, then we also have a small competitive ratio. And in the most ideal case, this competitive ratio is close to 1. On the other hand, we also want robustness. This is borrowing from the classical worst case analysis of online algorithms, where we want to have a constant gamma so that C of eta is at most gamma no matter how large the error eta is. And so on the slide is a stylized pictorial depiction of what an ideal C of eta curve might look like, where when eta is really low, we're close to 1, and as eta increases, our C of eta also increases, but never surpassing the upper bound of gamma. So this setup is enough for us to state our informal results. So as mentioned before, I continue the study of learning augmented online caching, and the results I show consist of an upper bound and a lower bound. The upper bound says that combining the naive blind oracle algorithm, which is possibly the simplest algorithm you can imagine for learning augmented online caching, with an optimal worst case algorithm, such as marker or LRU, depending on whether you want randomized or deterministic algorithms, improves on the state of the art. So combining blind oracle with the marker algorithm gives a better C of eta function than prior work. For lower bound, I show that combining blind oracle with LRU is optimal among all deterministic algorithms for learning augmented online caching. And so what this says is that this simple scheme of combining in a black box manner blind oracle with LRU is actually the best you can do, which may be somewhat surprising, given that previous algorithms were much more intricately involved with modifying existing worst case approaches. And here combining refers to applying online learning over online algorithms using either follow the leader for deterministic combination or multiplicative weights for randomized combination. So the next few slides, I'll formally introduce the model for online caching with predictions, and also discuss more formally the results that I show. So the classical online caching problem says that we want to serve a sequence of page requests, sigma 1, sigma 2, through sigma n online, while updating and serving our pages from a cache of size k. And so we have to serve every page from cache, but this cache is limited to holding at most k pages at any given time. To serve a page, if our page is already in a cache, then it's fast. We say that we serve the page for free. However, if a page is not in the cache, then we have to pay a unit cost to bring the page back into cache before serving it. And if the cache is full, it already has k pages. Before we bring our page that was requested into the cache, we also have to choose the page already in the cache to evict. And so this eviction is the key decision that the caching algorithm makes. In the online caching with predictions problem, this was introduced by Lycoros and Vasilevsky 2 years ago. Each page is augmented with a prediction for when the requested page, sigma I, will be requested again. And the measure of error, so the definition of eta, is L1 error, which means that eta is equal to the sum over all page requests of the absolute difference between the actual next arrival time of page sigma I and the predicted next arrival time of page sigma I. One small technical detail that I will gloss over is how pages that are requested for the last time are handled. But this is not important at all for any of the technical discussion. And so with this setup, the goal, as before, is to design algorithms that have good consistency and also good robustness. So along with introducing the problem, Lycoros and Vasilevsky also give a first algorithm for online caching with predictions. They show that there exists a randomized algorithm, which they call predictive marker, that achieves the competitive ratio of, so it's a min of log k, which is the worst case, the optimal worst case competitive ratio, and square root of eta over opt. In recent work, Rohatgi improves on this bound by showing that you can actually achieve competitive ratio that depends only on log k over k times eta over opt. And so in a regime where eta over opt is comparable to log k, the latter bound is better. In this paper, I improve on Rohatgi's result by showing that instead of needing a log k over k dependence, or instead of having a log k over k times eta over opt in the competitive ratio, we can get away with just a 1 over k times eta over opt. And so this removes the log k factor. But more than that, the algorithm that I proposed is also significantly simpler than the previous approaches, which are based on rather delicate modifications of the marker algorithm. So in contrast, the algorithm that I propose is a simple combination of blind oracle and some worst case optimal online algorithm. So this is just a classical algorithm like LIU or marker. Also want to note that the deterministic algorithm I discussed is also the first example of a deterministic algorithm for this caching with learned predictions problem. In addition to these upper bounds, I show a matching lower bound for the deterministic setting by showing that you must have this 1 over k times eta over opt term in your competitive ratio. And so this implies that the deterministic upper bound from the previous slide is tight up to constant factors. And so that concludes the presentation of the model and the results. For the remainder of the talk, I'll focus on the upper bounds and the intuition behind them. And for that, the crux boils down to understanding this blind oracle algorithm that is, in some sense, the naive algorithm that one can do in the caching with predictions model. And so what is blind oracle? To motivate this algorithm, it's best to think about the ideal world where we have perfect predictions. So eta is equal to 0. And with this assumption, it's equivalent to the offline setting, since perfect predictions means we have the full input. And so a classical result shows that if we have the full input, the offline optimal algorithm is given by the following simple scheme. So if we have a cache miss and a cache is full, then we simply evict the page that is predicted to arrive furthest into the future. This is exactly what blind oracle does, even if the predictions are far from perfect. And so what we do is we just look at the predictions for each page that we have, and we evict the page that we think is going to arrive, the page that is least closest to arriving next. To make this algorithm more concrete, here's an example execution of the algorithm, or here's an example input that the algorithm can be run on. So imagine that we have a sequence of page requests, A, BC, 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 and with the BCs continuing until our last request is an A. And suppose we're running this, we want to serve this sequence of page requests with a cache size of k equals 2. Suppose also that our prediction at time I is simply I plus 2. And so those are the numbers in the second row of the table. So it turns out that blind oracle actually has a cache miss on every request. The reason being that blind oracle thinks page A is coming very soon. And so it keeps page A in the cache the entire time. And then alternating requests for B and C cause thrashing of this cache. However, you can also observe that the error of the predictions is actually not that big. The only mispredicted page arrival is that of the first page, or sorry, that of the last page, where on the first request, we predict A to arrive at time 3, but instead it arrives at time n. And so the total prediction error is n minus 3. And so in contrast, the optimal offline algorithm only incurs 4 cache misses in total. And so it incurs cache misses on the first 3 pages, and then it incurs a cache miss on the last page request. And this shows, so this example shows that blind oracle is actually very far from robust, and that there exist simple examples where blind oracle gets the competitive ratio of blind oracle scales linearly in the prediction error eta. So if blind oracle performs so badly, why would you care about this at all? So it turns out that despite the bad performance of blind oracle when eta is large, blind oracle actually has pretty good consistency guarantees when eta is small, and in fact better than all the existing approaches. And so The theorem I show is that blind oracle has competitive ratio bounded by 4 plus 4 divided by k minus 1 times eta over opt. And although it's not on the slide, I also show a tighter upper bound when eta is very small, showing that C of eta actually approaches 1 as eta approaches 0. A sketch of the proof of this theorem is that I analyze the cost of blind oracle versus the cost of the optimal offline algorithm using a potential function that tries to capture the difference between the caches of the two algorithms at every point in time. And so this potential function is actually the combination of 3 different potential functions that together get the right notion of distance to obtain a tight analysis of blind oracle. And so with this algorithm, we're able to have very good consistency. But what remains is we still have to obtain good robustness. And so for this, we can actually use the more classical online caching algorithms that are worst case competitive. And so this is like LRU, marker, equitable, so on. And so if we want to use blind oracle when the eta is small, and these robust, worst case robust algorithms when eta is big, we have to figure out a way to combine 2 algorithms and somehow get the best of both of them. To rephrase this question slightly, we want to answer whether if we're given 2 online caching algorithms, A and B, can we obtain another online caching algorithm, C, whose cost is approximately the minimum of the costs of algorithms A and B. And so it turns out that online learning techniques work very well here. And so Fiat et al. showed that you can get a C that is a 2 approximation in a deterministic way. And it goes roughly just by following the algorithm that's doing better at any given point in time. So if A is doing better so far, I listen to A, and if B has better performance on the input so far, I listen to B. Bloom and Birch a few years later show that you can actually get arbitrarily close to the minimum while taking an additive hit in the cost using multiplicative weights. And so with a sufficiently small learning rate, you can get arbitrarily close to a 1 approximation. But you also have to have a 1 over epsilon term and additive cost. And so with either of these 2 results, you can take blind oracle and another worst case robust online algorithm and combine them into a single algorithm that is both very consistent and also robust. An explicit example of this is combining blind oracle with LRU using follow the leader. And so this algorithm actually turns out to be remarkably simple to describe. If we have a cache miss and the cache is full, we look at which of blind oracle and LRU has had fewer evictions so far on the request sequence. And so if blind oracle has had fewer cache misses, then we evict the page that is predicted to arrive furthest into the future. And if LRU has had fewer cache misses, then we evict the least recently used page, and that's all there is to it. And it turns out that this simple description is optimal up to a constant factor in the competitive ratio among all deterministic algorithms. And so similarly, if we combine blind oracle with multiplicative weights, blind oracle with marker using the multiplicative weights update rule, we'll get an algorithm that improves on those state of the art relative to previous approaches. So that's all I had for the main technical portion of the talk. And so I'll finally summarize the takeaways from this work. So at the highest level, I believe that augmenting predictions onto online algorithms can be a very interesting and useful approach to looking at online algorithms beyond the worst case. So in recent works, this has been applied to caching, scheduling, and various other problems. And these all have the property that they don't make these models don't make specific structural assumptions about the input, but rather focus on having a predictor that is black box that works for some set of inputs. And so within this framework, what this work shows is that for the specific problem of online caching with predictions, the simple thing in some sense just works. We can obtain consistency and robustness separately, and then combine these two modular components into a single algorithm with classical results about online learning on online algorithms. And so this simple approach, despite how bare bones it is, actually has better theoretical guarantees than the more intricate approaches that have been explored to date. Also, somewhat surprisingly, is that the simple approach yields an optimal deterministic algorithm that, combining blind oracle with LRU, is optimal up to a constant factor for deterministic online caching with predictions. And so I'll also leave you with an open question, which is whether you can beat blind oracle using randomization and to obtain an optimal randomized algorithm for online caching with predictions. In this direction, Rohatgi has a recent result that also gives a randomized lower bound that has a logarithmic dependence on eta over opt versus the linear dependence on eta over opt that I show is tight for deterministic algorithms. That's all I had prepared for today. Thank you for listening.